the practice exam, and I talked to the coordinator about this. Basically, what she intended is what's there. So basically, it's not like last time where you had a like it actually looked like a Canvas quiz. Basically, that practice exam Canvas quiz is just it's just a placeholder for that PDF file. So if you're able to get to that PDF file, that is what she made available. So basically, how many questions are in here? A lot. I think it pretty much goes section by section. But Clement, you believe some answers are wrong? Yeah, what question?
Just it's like yeah, basically 19 through like 25 or something.
All of them?
Yeah, or 24. They have like, I'll show you. They have like two functions, subtract and square, rather than each one individually squared. They use it for answer. And I checked with both not like that's like the
Okay.
function would be 4 and the bottom function would be x squared.
Oh, so it's not like the function is 2 and x? Okay.
No, it's
Okay. If that's the case, and so let me just pick one of these out. So let's look at 20. So the region bounded by that parabola, the y-axis.
instead of squaring them individually, it's squaring them to get that like, middle term. You know what I mean?
Yep. Okay.
That's the answer.
Yeah, I agree. All right. So this is not my file. I will see if I can correct those what 5, 6. But yeah, you're absolutely right. The radii should be squared individually before you find their differences. Sophie?
I'm at the very top. It says it's
Very top of the page or the whole
very
document?
top of the whole thing.
Okay.
Like number 1 through something.
Yeah.
Was it in like algebra, behavior? Is that like conversion and diversion? Or is
Yeah.
That, oh.
Yeah. So like without not graphing, because a graph would make that evident as well. But basically do it by hand. Go ahead.
Remember?
So Laplace transforms are not the important thing there, but basically, if I were to have left off this Laplace transform thing, which if you're done believe this is a thing you'll do at some point, but probably haven't seen it yet. Basically, the crux of this is to evaluate this integral. So what does it mean for L of 1? Basically, they're telling you what f of t equals.
So you just like plug in 1.
Yeah, so basically, part A is to find this integral, the integral from 0 to infinity of e to the negative st dt.
Okay.
So like the Laplace transform is just kind of a context for putting this improper integration thing. I don't need you to know anything more about Laplace transforms. It's just it's an application of derivatives over an infinitely long interval. Anything else? Okay, I have one last big idea to go over with you on series, and then we can go back to talking about review stuff. So at the very end of Friday, we talked about this harmonic sequence, or the harmonic series, sorry. Basically the 1 over n. So basically this sequence, now we talked about two things, two related ideas, what the sequence does and what the series does. So the sequence 1 over n, as n gets really, really large, let's just reset the stage here. Are we okay with the idea that that sequence converges to 0? All right, so that's a different idea from what the series does. So we talked about what the series does. So the series as in starts at 1, goes to infinity of this. Basically, the logic I presented to you last time was that basically, no matter how small these terms get, I can always pick a finite number of them and make something that's at least a half. And because of that, this series diverges, it goes to infinity. So even though the underlying sequence goes to 0, the underlying or the overall series does not converge. So very specific series where this happens, but we'll make sure we're okay with that. Any questions on the harmonic series? Okay. So one big theorem that comes out of this that's going to help us kind of answer these questions about convergence and divergence. So let's assume that I have some series that converges. Basically, when I take all the terms in that sequence and add them all together, them all in vague quotes because there's an infinite amount of them, but basically that sum converges to some number. Can I say anything for certain about the underlying sequence? If the series converges, can I say anything conclusively about the sequence itself? So what am I doing with the series? Sequence and series are related things. But what's the difference between A sub n and this series that involves A sub n? Right, instead of just, so in the sequence, what am I doing? I'm A, B, C, D, whatever these terms are, as opposed to the series where I don't care about the individual terms as much as I care about what their sum is. So if I know this series adds up to something, which is, I don't know, capital L. So basically, the more and more I add up those terms, the closer they get to some number L. Can I say anything about the terms in the sequence? Like as I go far into the sequence, what has to be true about the terms of the sequence? Go ahead.
The sequence converges to 0.
The sequence converges to 0. How do we feel about that? Does that make sense? If the series converges, then what has to be true as I add up all these terms? They have to get smaller and smaller. They have to diminish enough so that really I'm going to keep adding stuff forever. So I have to be adding things that diminish to the point where it's not making an appreciable difference to that sum. So because of that, a very powerful theorem that comes from this. It's called the divergence theorem. If you have a series that converges, doesn't matter to what. If the series converges, then the sequence underneath it converges to 0. That has to be true. So let me ask this before we move on. Is the converse of this true? Can I reverse this statement? Let's say I have a sequence that converges to 0. Does that mean the series converges? So it shouldn't, right? I just showed you an example when that is not true, right? So if I scroll back a few things here, this is one of those times, right, where the sequence goes to 0, but if I add up all those terms, it doesn't converge to anything. So in one direction, this thing's true. So if I have a series that converges, then the underlying sequence has to go to 0. What can I say that goes with this, though? What if the sequence is anything other than 0? What does that mean about the series? It has to diverge, right? Because let's say the sequence goes to 1, then what's that mean about the series? Basically, you're going to be adding numbers close to 1 to it with every successive term, so it can't converge. So a couple different ways to think about this idea. If you have a series that converges, then the sequence has to converge to zero. And kind of going at it from the other direction. If you have a sequence that does anything other than converge to zero, the series cannot converge. How are we doing with this idea? So it's a pretty quick way to tell if a series diverges. If you can kind of fail this test here. So let's see an example of this. I'm telling you this series right here diverges. So I'm already telling you the answer. So now we have to prove it. Like, make me an argument that this series diverges.
Converges to 1/5. Facial limit,
So you're saying the sequence, what sequence is that?
n squared divided by 5 times n squared plus 4.
All right, so you're taking the series out of it. You just want to look at the terms. Basically, I want to look at the nth term of this sequence. You already had an idea of what this converges to, which is 1/5. How'd you get that?
Divide the numerator and denominator by n squared.
Right, so I will, or depending on how you want to look at it, multiply by 1 over n squared over 1 over n squared. This becomes this new expression 1 over 5 plus 4 over n squared. And that goes to what? 1/5. So I know that the sequence goes to 1/5. Am I done? Is that enough for me to prove to you that the series diverges? Absolutely. So the limit of this sequence is 1/5. More importantly, it's not 0. Do we know this symbol here? Don't ask me why. That means therefore. Therefore, this series diverges. But yeah, that theorem, so it's not good for proving the series converge. It's not something that you can't use that theorem to show that. But if you have a series that diverges and you can show it by the sequence having this bad behavior, that's enough. That is a sufficient way to show that that series diverges. Or better yet, if I don't tell you what the series does, that's a pretty quick way for you to at least test and maybe find that out. Questions? All right, that's all I have for you from 8-2. So as I said last time, I forgot to say this in person. I put it online. I cannot hold office hours this Friday, but for you, it wouldn't be especially useful this week anyway. I'm holding office hours today from 11:30 to 1:30, and Wednesday at the normal time. And then I will not be in the office on Friday. So if you can stop by after class today, I'll be there for a while. All right, so we talked about this answer key having some issues. Having said that, though, I think the questions in here are relevant and useful to work through. Any questions in particular you want to talk about? Or, by the way, from this or anything else, really? Go ahead. Edie.
I was wondering if we could go over some of the ones in 8.2.
On this document?
Just in the workbook.
Sure.
Anyone that's like maybe one of the later ones, but like
Okay.
not one of the earlier ones.
How about this one? Okay. All right. So it says determine the sum. It's not telling you it's not asking you if it converges or diverges. It wants the sum, right? Is that better? Okay. Can I actually annotate? All right, so I have to narrate a little bit. If they're asking us to find the sum, like I think I said this on Friday, but I'll remind you. It's one thing to determine if a series converges. It's a much harder thing to find the sum in general. There are only like very like specific kinds of series that we understand well enough to figure out their sums. So what are those types? Geometric series is one. The telescoping. That's basically the list. There are others, but we talked about those two. Is this either of those? I think technically it's not geometric, but I can kind of manipulate it so it becomes geometric. Is that a big enough sense? What can I do to this to treat it like a geometric series? I can split up the fraction. So instead of writing it like that, because I think technically if you write out some terms, that doesn't work. But what if I do this? This series of 3 to the n over 9 to the n, plus this other series. Individually, are those geometric? Yes, they are. Okay. We have a good idea how to deal with geometric series. Now we have to ask ourselves this: do those converge? Both of them. They both have to for the whole thing to converge, right? Why do they converge? Okay, what's this ratio of the left one? 1/3, 3/9. And this one? 5/10. So yeah, both strictly between -1 and 1, so they both converge. So how do I get sums? So what is the first term of this first series? Yep, I plug in 1, I get 1/3 over 1 minus 1/3. So that comes out to and then similar thing over here. No. So one of them converges to 1/2, one of them converges to 5/4. So that's 7/4. Does that answer? Oh, wait, you're still working on this one, never mind. And this is something that is not too uncommon for geometric series, is that maybe the thing I give you is not geometric. Like, I don't think this would be, but you can manipulate it so that you can analyze it that way.
The S equals like that rule, which it only works for geometric.
It only works for geometric series, and it only works for like very specific geometric series. Yeah, right. If R less than 1 or what, and what?
Oh, it's like, it can't be like 2 or something.
Right. So it's not enough for it to be less than 1. What else has to be true? Right, it has to be strictly between these two. So yeah, this right here, it's a very nice formula, but it's very limited in the things that it works for. It has to be a geometric series, and it has to be one that actually has a sum, actually converge. I don't believe so. But
Can you go over the monotone and the boundary?
yeah. So like what they mean?
Yeah.
Yeah, what is a monotone? And we talked about them in terms of sequences. What is a monotone sequence?
Something that's increasing,
Increasing or decreasing, right?
or decreasing.
Yeah, but it has to do one of those things. So let's talk about counterexamples. If a sequence is not monotone, what does it look like? Like, what does it do?
It's like a cycle, like a sign up or something.
Yeah, like, so it means it increases and decreases, right? So basically, the thing that's gonna stop a sequence from being monotone is that it has increases and decreases. If it only has one or the other, that's monotone. So. Now, I told you a lot that really sequences don't look like this because they're not defined in between the integers, but aside from that, go with me here. Is that monotone? It's monotone, right? Because what? It increases, right? It's diminishing, but as far as I drew it, it increases. What would I have to do to fail the monotone test here? Now it's not monotone, right? Because at some point it starts to decrease. So that's the idea of monotone. If it increases or decreases, never both.
Something that has that telescope.
Yeah.
Thing that's not monotone, right? Is it? Because it's like sometimes.
The sequence might be the series. Actually, if the sequence is monotone, the series has to be monotone as well. But in terms of like, thinking about telescoping series, by the way, telescoping sequence is not, can't really talk about a telescoping sequence because the reason it's a telescoping series is because those middle terms, when you add them together, they cancel. In a sequence, I don't even add those together. I'm just looking at the terms themselves. So because of that, the most direct way to get the sum of a telescoping series is to basically write out the terms and try to understand where those cancellations are going to happen. It's almost always going to be in the interior.
Will we see that on like an exam?
You may. So I think there are a couple on the web work. There are a couple in the problems from the textbook. There are probably a couple in that document too. But I think the most direct way is to write out the first, I don't know, 5 terms, however many you need to kind of understand it. If you start seeing things cancel out, like on a regular basis, that's a pretty good indication that you're dealing with a telescoping series. Maybe is there one in that document? Probably at the bottom of it. Oh, really? So it's not in order?
No.
Why would it be?
It's probably like, yeah. Volumes and then put like the work stuff in here.
Maybe the fact that I don't see one.
Is it that?
I don't see one. I'm gonna let that speak for itself.
Can you go down up a little bit?
Yeah.
That 29.
29. I don't think that is going to be a telescoping sequence, but I think it's worth talking about. Let me hold that thought. Go ahead, Sophie.
For those ones where you're again just doing if it's divergent or convergent, or do you need to do like right if it's bounded in monotone?
Oh no, when you see that describe the behavior, I'm just looking for convergence or divergence. And the one specificity you might be asked for, if you're telling me it converges, yeah, tell me to what, especially if it's a sequence. So, I just said with geometric series, you can get a sum of a series. That's usually not true. But with sequences, you can get their limits. If they converge, you can get them. You want to talk about 29? So let's let that be the standard. If the sequence converges, tell me what it converges to. -29, you said negative, said, what was it again?
-4.
-4, how'd you get that?
We split out the denominator and then like we sort of cancel out 3x plus 1, which like 3x plus 1 in the denominator.
I'm gonna push back on you canceling because you can't technically do that, but let's,
If you look at the,
this in parentheses.
with this term.
So if I expand that, I get what, 12, -12 n squared? -4n. So plus 17n. -7. All over 3n squared minus 1. Okay. So if I want to find the limit of this, are you okay? It sounds like most of you are okay with if I just say -4. Are we okay with that? Or should we go into why that's the limit?
You go with it.
Yeah, absolutely. How can I get there?
Biggest terms,
What's that?
biggest, terms, and
So that's good intuition on why it comes out to -4, but we can't really cancel that way because I have other terms going on, right? So but I think a really good method to rely on here is look at what the largest powers are. Yeah, what's the degree of this numerator? 2 and 2. So because of that, I'm gonna divide by n squared over n squared. And maybe, let's be clear about why I'm doing that. If I let n go to infinity on all those terms, what happens? A lot of them go to infinity, right? Like all of them. But if I divide by n squared over n squared, I get what? -12 plus 17 over n minus 7 over n squared over 3 minus 1 over n squared. Now, if I let n go to infinity, what happens to all those terms that vary? They converge now. So all I had to do was to do that one little manipulation, because all these individual limits here don't exist, but here they all do. So this limit comes out to be -12 over 3, which is negative.
So does the series just diverge and it's equal to 0?
So let's finish part A first. What's the sequence do? It converges to -4. That's good. What does the series do? It diverges why?
it's less than negative.
Not less than -1. That's a different thing.
Keep adding -4.
Right. So the sequence goes to -4. The series diverges. Yeah. What if this went to like a half? It still diverges, right? So I think you're getting the geometric thing.
That's not zero.
It has, so yeah, go ahead and. Okay, let's talk about that too. So, hold on, let's answer this question, and then we'll start modifying. So, the answer to A is that it converges to -4, right? That's what this shows. What does the series do? Okay, let's be really clear, why does it diverge?
Divergence.
What is the divergence test or divergence theorem say?
Limit and kind of approaches infinity, they find is not equal to 0.
Right.
Series.
It's just because since this is not 0, the series has no hope of converging. Because I'm gonna be adding things very close to -4 to the sum with every passing term. Right.
For the test, can you just put -12 over 3? Do you have to do all the work?
If you're on a free response, I would show you some work just to kind of cover yourself. And really to argue the point. If it's multiple choice, as much as you need to convince yourself. So let's say this now. Let's say I went through all this limit stuff, and here's an easy way to do this. Let's start over. Let's say this is just -12n. What does this sequence do now?
Equals zero, converges to zero.
The sequence converges to zero, right? I can do the same kind of thing. I can still divide it by n squared over n squared. And then what does it look like? I'm gonna combine the first two terms with 5n. So this becomes 5 over n minus 7 over n squared over 3 minus 1 over n squared. So what does this go to? 0. So the sequence converges to 0, right? What does the series do? Does not, it actually doesn't converge. So this is not the thing that will be on the test, but I want to be very clear about what the divergence theorem tells you. The divergence theorem only really helps if the sequence goes to something that's not 0. If the sequence, if the sequence goes to like anything other than 0, what does the series do? If the sequence goes to 0, the divergence theorem doesn't tell you anything. It fails to give you any conclusion. We'll learn after the test that how to figure out for sure that this series diverges, but for right now, don't worry about that for Wednesday. I'm just trying to point out that don't do more with the divergence theorem than it's actually written for. It really is helpful if the sequence goes to something that's not 0, but other than that, it's not very helpful. But
Can we do like 41?
41
Yeah, I just wanted to.
hemispherical tank.
Stand up 7.2 after.
I could. Go away.
Yeah, this sounds like-
Oh, good.
I don't know, if something important information on there.
It's resting upright on its curves. Oh, okay. I'm gonna go a little bit rogue and say that 41 is not worth your time.
Do like 21, this like one. I think it's 40.
How many of these type of questions do you have?
They're very long, so it's not gonna be many.
Their response?
It could be. Sorry, some of these I gotta hold a little bit back, but
Are you able to tell us again if like how many are multiple choice?
yeah, it's 10 and 2 again.
10 and 2 again?
Yeah.
Are we given any formulas or anything? Or is it-
I don't believe so. I can look, but I don't. I can't think of anything that might be on there that you would need. All right, so tank in the shape of an inverted circular cone. Let's do part A, and I think that'll be good. So inverted circular cone. What are the dimensions of it?
I think it's 4 meters, it takes 20,
So,
and then it's full.
okay. Full water?
Yeah.
Am I taking it all the way to the top, or like there's some, no, there's a
It's
about straw.
1 meter, but
So. All right, cool. Now what? So let's just say that in general, what's the integral I have to do to find work? So basically it's a force. It's some product of forces and displacements. So I gotta figure out the force here. Basically I'm lifting masses, so
square, I'm just trying to picture, is the tank like, it's completely full of water, right?
Yeah.
To the top and then we're trying to find where that takes in.
Yeah,
Okay,
but all the water is basically lifted above the surface out this spout here.
Find an equation for the volume or
Okay.
function for volume.
Okay, so
It counts.
what kinds of like shapes of like water am I gonna take out of here? They're gonna be, so let's talk about the variable. I think it makes sense to talk about cylindrical discs. We've been calling this X or Y, I don't remember what we did.
Call it X.
Alright.
Doesn't really matter.
No, it doesn't, I just don't wanna put some more wrinkles in, but, yeah, variable, the change in your independent variable. So basically, I'm looking at cylindrical discs of water. How do I find the volume of things like this? Not pi r h, well, pi r squared. So I'll be specific. This radius is gonna be a function of x. The thickness is gonna be dx. So now what I have to do is figure out how to characterize that radius as a function of x. So the radius is gonna change with height, right? The nearer the top of this thing, you're gonna have larger radii. But now we gotta be specific about how that happens.
Divided by 20,
What's 45 about 20%?
the ratio of the change in the radius.
So-
on the height.
One thing that I kind of encourage here is to make these tables. So x is my independent variable, r is the thing I want to try to make a function out of right now. It probably makes sense now to talk about what x means. So where is x equals 0 on this thing? On the bottom? Oh, see, now we're fighting. Here's the real good news, as long as what you're doing is consistent, it doesn't matter. Well, I think that's a class we're mostly doing top, right? Okay, so don't be mad. But let's call that x equals 0. When x equals 0, what's the radius? 4. All right, what's another x value?
20.
Just go extremes. So if x equals 20, r equals 0, right? Is that enough? Can I assume this is gonna be a linear relationship?
Yes.
Why?
Straight side.
Straight side. So the hemisphere kind of falls apart there, but we're not, took that off the scope. So I think those 2 points are enough to get me a function here. So straight line, y equals mx plus b. What's our slope gonna be? -4/20. Or -1/5. And I get the y-intercept. Yeah, should be 4. One of the points we chose from our table is the y-intercept. So I think because of that, we have y equals -1/5 x plus 4. But really our y is our radius, right?
Can you
So-
go over how you got 4 again?
Yeah, so the 4 is the y-intercept, right? So basically what y is equal to when x equals 0. So that, we got lucky, that happened to be one of the points that we dealt with.
So if you were to use like x equals 0 as like 20,
So if you did x equals 0 at the bottom here,
you have to use 20.
basically you would get an integral that looks very different from the one this one, but if you calculate it, you'll get the same number. It really is a personal preference thing. So I think now we have our volume function. Volume equals pi times -1/5 x plus 4 squared dx. That might be the most important part of this whole problem. There are a lot of important things to kind of figure out, but that's a big one. Now that we have the volume, what do we do?
Find the mass, and it's like that, that's.
How do you find, okay, so. What do I do with this volume to find the mass? Running out of room, so maybe I'll just edit this way. Mass is equal to 1,000 times this. Now what? How do you find the force of the mass? Wait, why do we have to do gravity here when we don't always have to? But like, that's a number I kind of expect you to have, so. If that wasn't there, would you still have to find gravity? That's not the reason. It's all about the density. What is the density written mass here? It's a mass density. When we're in imperial units like feet and pounds, we don't deal with mass. We have a volume or a weight density. Certainly. The zero that I was trying real hard to fit in is the one that didn't. So there's our force function, right?
Yeah.
So, cool. We got our force. What else do we have to do here? Find displacement. So that involves a little bit of special care because we're not just lifting this to the surface, right? We're lifting this beyond the surface. So for now, we got the force though, so I'm gonna put that in here. 9,800 pi times -1/5 x plus 4 squared dx. And now we're gonna figure out the displacement. I'm gonna just figure out the displacement first with bounds. A simultaneous vote for either one. Let's do bounds. What are the bounds of this interval going to be? 0 to 20, right? Here's x equals 0. How much of this thing do we want to empty out? So here's why it can't be 0 to 21. What does the x stand for? It stands for the height of the water, right? If you have an interval that goes from 0 to 21, you're saying that I'm pumping out 21 meters of water, which I'm not actually doing. So the bounds are 0 to 20, but I suspect you're correct. You have to worry about that extra meter that I'm pushing in, right? So how do I account for that extra meter? Let's think about it this way. We made a table before, right? Now let's do another table. X versus D, displacement. If X equals 0, so the water on the top, how far does the water on the top have to go? A meter, right? Give me another X value. 21, there is no X equals 21. How far does the water, so that's the water at the bottom, right? How far does that water have to go? Does that help us come up with what the displacement is? What is it? X plus 1, right? So for whatever X value I have, water has to travel 1 meter on top of whatever its like height is.
You're just multiplying by this one.
Yeah,
You still taking an interval of that?
yeah, if it hurts your eyes. But I think that integral is perfect.
Yeah, so he's a bit different, that's the main reason I asked for this question.
So here's the thing, the answer key is probably different because I think
They use X at 0.
they use X equals 0 down here, right? So here's what I'm saying, your integral will look different than that if you do this. If you compute it, it will be the same.
So we'll do the base function, we also got y squared over 25.
Y squared over 25?
Not really sure about that.
That's because they defined X down here, X equals 0 down. But here's what I will tell you. Let's say hypothetically there was a question like this on the exam, and all the multiple choices looked like they would look like if X was down here. But like I knew that we didn't really go over it this way. I might have rewritten all the multiple choices to make sense for you.
Will this work if you give like the balance from -120 and then make it
No, because if you go from -1 to 20, then you're saying that this thing is 21 meters high and you're displacing water through all, like, so it doesn't quite. I think you do have to have the bounds be a 20-meter wide thing. Sophie, I'm sorry, you asked for a question from 7-2.
It's fine.
Are you sure?
Yeah, I can just look at the videos. But
Okay.
if, say they only have like 19 meters of water, the bound would just be 0 to 19, right?
Yeah, so that's a good question. Let's say this. Let's say the tank has this exact shape, but it's only filled up to here. And this is like 16 meters. How does that change what we've done? The bounds would be from 4 to 20. Okay, that's one change. What else would change?
+5.
Would you do X plus 5? Let's think about it. What does X equal right here? How far does this water have to go? 5. I still think X plus 1 works.
So you can't do 0 to 16 if you do 4 to 20.
If you could do 0 to 6, so it has in. I think these are probably unsatisfying answers, but I think you could do 0 to 16, but then you'd have to alter that X plus 1. So let's think about that. So you're gonna start pumping out the water here, right? So I think you're saying that this is X equals 0. Does that make sense?
Yeah.
So if this is X equals 0, how far is this water going? 5 meters. So what do you have to do to this thing, this integral? Where's the change happen? X plus 1 becomes X plus 1.
In this case, I'm sure the assumption also be different. Since
Yeah, that's true, too.
0.
So a lot of things are gonna have to change, and as long as they all change in the appropriate way.
So just do 4 to 20.
I mean, or
Yes.
really,
Yes.
those are all good questions to ask at the very beginning. It's really hard to make all the necessary changes like downstream. But really, you have a lot of freedom in terms of how you set these integrals up. And they're gonna look very different, like the setups are gonna look very different, but if you do everything correctly, there's only one correct answer to this. There's a ton of ways to get to it.
Can I set my displacement as just X and then I can put my neutral bounds as 21 and 1? Does that work?
That's better. You go, let's look at it. If I go from 1 to 21, and this term is just X dx. Where is X equals 0 for Ethan? I mean, you don't really care where X equals 0 is because you're not integrating there, but if you do this, where does X equals 0 have to be? Well, let's answer this first. Where does X equals 1 have to be? Right here, right? Where's X equals 21? So then where's X equals 0? X equals 0 is the spout, right? Okay, so you're trying to move all this stuff to the spout, right? Does your displacement thing of X make sense for you? How far is this water gonna have to go? 1 meter? That equals X. How far is this water gonna have to go? 21? Yeah, I think this works.
About the radius.
The radius also has to change. Yeah, we're just talking the displacement though. If the displacement's fine, that radius was very much dependent on us choosing X equals 0 where we did that. So if you move that, you have to make a lot of changes. So there are a lot of things that are good to think about at the beginning, but like I really advise, especially if you got 50 minutes to do this, whatever decisions you make first, try to stick with them, unless it's just not making sense. Question?
Where's the X from X dx coming from? At the end of the-
Yeah, so here's the thing here. The force comes from everything I'm about to underline. So because that weight came from the volume is the thing that had the dx, the change in x tied up in it. So the displacement actually comes from static X values, not, it has nothing to do with X. Sounds like it's 11 based on what I'm hearing. How we doing? So I'll be upstairs in half an hour. If you're free, come see me. Otherwise, drop me a line on email or something, but otherwise I'll see you Wednesday.